Okay, good morning, everyone. Today we're going to have a coding practicum on graph algorithms. And we're looking for a volunteer who hasn't gone already. Or I can just give you the assignment, let everyone do it themselves without the in-class guidance. Okay, Sheng Li, you just went in the other class, right? No. Or why don't we spread the wealth here? Give Sheng Li a break. He just went in 3:55. So yes, Daniel, I have you recorded as having gone on July 6th. We might need to come back to you, but we have 46 students in the class. Okay. Dava, you also went the other day, right? So I appreciate the same people volunteering multiple times. All right, I guess we'll go back to Daniel because Daniel went earliest of all the others. So Daniel, if you want to share your screen. This is a new assignment. Yes, this is a new assignment. It has not formally been assigned yet. I'm going to get you started. It's on graph algorithms, then you'll have a piece to work on yourself. Okay, so you need to go to PyCharm. The official due date for zyBooks is next Friday. So even though you should really do it before the exam, but we'll give you Friday. The exam will rely on concepts, but there is one question that's, at least one question that's directly related to the overall framework for the assignments. And then some other ones may relate to the specific problems in the assignments. All right, are you creating a new project or you just create a new file? Tell us what you're doing here.
It was a file. Do you want me to make a project?
No,
Okay.
I don't need a new project. Okay.
Okay.
The only thing is, this is probably not the best example. So if you could take one of the other ones with the graphing stuff in it as your, oh, this one has a graph also?
Which one?
Assignment 6 has a graph.
Sorry, 1 second. I didn't finish assignment 6 yet.
All right. So, but do you have all the code there in general or no?
I think like just the functions, but Not the graph.
Okay, I don't know, whatever.
the table.
Create a new function, as long as you have the other stuff available if we need it. So create a new program. Assignment7.py. Use one of the existing ones as a starting point.
Okay. Can I just leave it as class for now? So should I
No,
copy all the
call it assignment 7 and make a copy of a previous assignment. So one of the reasons we work so hard on creating these templates is so that you have them as a starting point for the next one.
So should I just copy all the code from?
We just take one of the existing assignments. But we want, the stuff with all the, the template code with the plotting and all that. Okay.
This should have everything.
Fine, good, go up. So change that to assignment 7. We're on assignment 7, right? This is 7. Well, line 3 also. And we'll call it graph algorithms. Okay, you can delete the LPSST. You can delete that function.
And that one.
And that one.
And all these too.
And yeah, you could delete that.
Okay.
And the process file. Okay. All right. So the first thing we're going to do is we're going to create a text file. Why don't I see assignment 7 on the left side?
Over here?
No, on the left side.
Oh, because this is just a file. It's not a folder or project or anything.
That's unusual. Okay, fine.
Yeah, I have to open a new. I would have to open the.
All right, as long as it works, I guess we'll.
It should work, yeah.
Okay, fine. So we need to create a new file, a new text file. Can you create a new text file, please?
Yes. I guess I'll do that here.
You can't. Why can't you do that in PyCharm?
I never tried it there.
Go to the file menu. New.
Oh,
file.
I guess we could. Okay.
We're going to call it graph1.txt. Okay, and we're going to make some zeros and ones in here. So this is going to represent a graph. We'll start by making it a complete graph. Okay, so 0, space 1, space 1, space 1, space 1. Okay, on the next line, 1, 0, 1, 1, 1. This is going to be a complete graph of order 5. Okay, 1, 1, 0, 1, 1. Next line, 1, 1, 1, 0, 0. And finally, 1, 1, 1, 1, 0. No, sorry, 0, 1. Previous line. Okay, I guess you can leave the cursor there. Okay, fine. Let's go to your assignment. Create a function called readGraph. Okay, and it's going to get a file name. So you're going to provide the file name of the graph file, and we're going to read that. Okay, so the first thing we need to do is open the file. So you say with open. the file name
Sorry about that.
as file, colon. Okay, and you could say, for row, I'm sorry, file equal, row equals I'm sorry, let's do this. For line in file, or line in file dot read lines. Okay, good. And you could say you need a colon. Okay, so now we're getting a line of the file. So we want to turn that into ones and zeros. Okay, so let's create a variable at the beginning of the function called graph. Okay, and it's going to be an empty list. Good. Okay, so what you're going to do is you're going to split the line. Okay, so you can say row. No, let's not call it row. Let's call it S equals line dot split. You're going to split it on the spaces. So put a quote space. Good. And then you could say for SS, these aren't good names, but for SS and S, colon, you need a variable. Okay, so before the S equals, a row equals a empty list. Okay, and then over here, you're going to say row dot append row append, and you're going to append the int of SS. Okay, good. And then you outside that loop, outside the loop, no, not that loop, the inner loop, outside the inner loop. So indent one.
Okay, here.
Okay, so you append, so graph dot append the row. Okay, and now you could return graph. Don't do it there though. Okay, good. So here's what we're going to do. Go to your main program. You can delete all that stuff. And you're going to call read graph. You could say graph equals read graph, or G1, better yet, G1 equals. And pass in the name of your file. Now, someone raised on the chat, is your graph in the same directory? I'm going to assume it is, but I don't understand why it's not showing up on the left-hand side. And it's a string, it's a file name, so it's a string.
Here. Yeah, it should be here.
Okay. So that's a string, it needs to be in quotes. And then you could print G1. So if it works, we're going to get, and you can run that.
Oh, I forgot to do that. Okay.
Okay, so we got a list. Okay, you just made an adjacency matrix of the graph. Okay.
Mm-hmm.
All right, good. So let's actually change the name of that. Read graph as ADJ matrix. Okay, so rename the function.
As what?
As, you know, just leave it as read graph, it's fine. Okay, let's write another function called convert to ADJ list.
To what again?
ADJ table. All right, and you're going to pass in a graph. All right, or yeah, that's fine. Okay, so what does a table look like? It's a list. It's a list of lists, basically, right? So you could say ADJ table equals an empty list. Okay, and now what you could do is you could say for I in range len of graph. Actually, the right way to say it would be len graph bracket 0. So that'll get you the length of the row. No, len of graph is good. Len of graph is good, just without the 0. Without the 0. Yeah. Okay, good. And we're going to say row equals graph bracket I. Okay, so we're getting that particular row. And now we're going to loop over that. So you could say for cell, how's that? For cell.
Should it be in this for loop or?
Yeah, right there. No, yeah, for cell in row. Cell CELE. Okay, so we're going to check, right? We say if cell, better yet, let's do it like this. I think it'll be more clear. So you could say for I, for J, instead of for cell, for J, in range len row. So that's going to be our column now, right? Okay, so you could say if graph bracket I, and then another bracket J, right, equals 1. Okay, then you need a colon, yeah, then you're going to add it to the list. So you could say, you could create another variable before the list called neighbors. No, not there, inside the inner loop. So right after the row. Neighbors equals an empty list. Okay. And you can say this. So you could say if then you say neighbors dot append J. Okay, good. And then you're going to, after that for loop, and then, yeah, so you're going to say ADJ table append neighbors. Okay, and then return ADJ table. Okay, so now go to your main, and instead of G1, you're going to call it AM1 for adjacency matrix 1. AM1, pass that into the print. And then we're going to call the function, we're going to say AT1 for adjacency table 1 equals convert to adjacency table AM1 and print AT1. Okay, so let's run that. Okay, so everyone see, okay, so look at that. You see what we did there? Okay, can someone tell us what we just did in English? So the first line, we have an adjacency matrix, right? So we have ones and zeros. And the second one, the adjacency table. We have a list of all the neighbors. So the first vertex is adjacent to 1, 2, 3, 4. Second vertex is adjacent to 0, 2, 3, 4. Third vertex is adjacent to Z1, 3, 4, and so on. All right, let's make two more. Well, let's make one more, the edge set. Let's forget about the edge hash, the hash map. So let's create another function. You can copy this one if you like. Copy the one we just made, and we'll call it to convert to edge set. Okay, so create a variable called edge set instead of adjacency table, line 55. Okay, and get rid of line 58. Good, and you're going to say in line 60, if the edge exists, you're going to say edge set dot append. Okay, edge set dot append. You could put a tuple in, so parentheses I comma j. No, you need parentheses, the tuple.
Oh, okay.
Like that, exactly. And then get rid of line 61 and return the edge set. Okay, and now go to your main and add that in. Okay.
Actually, it's, yeah. So that's AM1, right?
Right, correct.
And then,
So this is just going to be the edges without broken up by vertices. Okay, you can run that. Okay, that looks good. Okay, maybe we should put a comment before each one. So go back to the code in line 69. In line 69, in the existing line, before A1, say adjacency matrix colon. Good. You don't need a space because the print will put a space there.
oh, okay.
Okay, and do the same thing in line 71. Set to the right adjacency table instead. Good, and do the same thing in line 73. And call that an edge set. Good. Okay, now we're going to make this a little bit more flexible, okay, because we're also going to support quest matrices. So go back to your other functions, and we're going to say, go to the read graph. So we're going to say, all right, that one's good as is. For adjacency table, well, so just one thing to heads up, okay? In line, go to the adjacency matrix one, the first one. Okay, we're assuming, just stay in one place so we can read it. Okay, in lines 58, we are taking the integer. Okay, so we're going to assume that the costs are all integers, okay? Yeah? Otherwise, it's not going to work. Now, in line 48, we're assuming everything is 1 or 0. We're going to now assume that 0 means it doesn't exist, and greater than 0 means it has a cost. So in line 48, you could say greater than 1, greater than 0. If it was greater than 0, we assume an edge exists. Okay, good. And in line over there, we're going to do the same thing.
Here.
Yep. Okay, how do we store the cost though? So we're going to append that into, because we're going to be concerned with cost matrices here, okay? So in line 49, when you append a J, don't just append a J, append J in parentheses, because it's got to be a unit, okay? In parentheses.
Yeah, it's okay there. It wasn't letting me make another one.
Okay, so J and the graph I of J, which will be the cost. No, inside the parentheses, because you're treating it as a tuple, as a unit, right? So J comma graph I of J, which is going to be the cost. Good. Okay, and the same thing for the other one. You're going to have IJ comma graph IJ. We need IJ comma IJ. IJ. Good. Okay. No, part of the unit. It's IJ and the size. Okay, good. Okay, go down. Graph IJ is the cost. Okay, so instead of calling it adjacency matrix, we're going to change the word there to cost matrix. You can leave that. No, you can leave that. I don't care about that. The label. Adjacency matrix. Call it a cost matrix. And capitalize the M since you capitalize the other ones. Okay, good. Let's run that. Okay, what is it complaining about here? Oh, because now we have two things coming in. Okay, so we need to say if graph IJ bracket 0. I'm sorry, bracket 1. No, hold on. No, where's the error? Go back to the stack trace. Okay, it's the graph oh, because it's not a function. That's the problem. It's not graph IJ is not a function. It's a
yeah.
Got to do it like in line 48. Okay, same for line 60.
Yeah.
All right, so now we have it with the cost too. Yeah, everyone see that? Okay. All right, so let's code some stuff. Okay. First of all, we're going to make another way of making a graph. So instead of read graph, in addition to read graph. So make a copy of read graph. We're going to call it random graph. Okay, so what parameters do we need? We need a size, the size of the number of vertices, and we need a max cost. Okay, and we need we'll call it a probability of an edge. Okay, good. No. You know what? We're going to make all edges. We're going to make it have all edges. Just get rid of the probability of the edge for now. Okay, So here's what we're going to do. We have graph there. We don't need to open a file, so you get rid of lines 45 and 46. And you're going to make a loop. So you're going to say for I in range,
Oh,
and not indented, for I in range, for I in range, for I in range,
sorry about that.
size. And then inside that, you're going to say for len, for J in range size. Good. And let's put the row equals blank. Move that above the 4J. Good. Okay, and now we're going to say if I on line 48, get rid of 48 and say if I not equal to J. So we don't want any loops, right? It's not equal to J. Then we're going to make an edge. Okay, we're going to make an edge. So we're going to say cost equals random. You have random installed already? We'll find out soon. Dot randint. Good. We want it to be between 1 and max cost. Okay, good. And then we're going to append. So get rid of line 50.
This whole.
No, we need the row append. We don't need the for SS.
Okay.
Okay, so we're going to say row dot append. No, we need the row dot append. We're going to pass in. This is the graph now, so we're going to pass in the cost. Good. And the graph dot append the row, and we return the graph. Okay, wonderful. So go down. Okay, so I want you to comment out line 81, duplicate line 81. Control D, can comment out 81. And instead of regraph, we're going to say random graph. Random graph. And we're going to pass in the size will be 10. So it'll be a 10 by 10 graph. And the max cost will be 100. Okay, let's run that. Ooh, okay, that's a little big to look at. So let's make it 5. Leave the 100 because that's just the max cost. Okay, run that again. Okay, so something is wrong here. Oh, yeah, you know what's wrong? We need zeros for the non-existent edges. Okay, so go back to the code. So where is the random one? Okay, so we're going to say as follows: if I equals J, over there, if I equals J, right there. No, where you are.
Oh, equals.
If I equals J, then row dot append 0. Else, we make a random one. Okay, good. Let's run that. Okay, so we have, why do they all look the same though? You see what I'm saying? There's way too much going on there. Oh, because the graph dot append row is indented. Go up, go up.
I see. So this.
Run that again. That's better. Okay, so you see we have a random matrix now. You see that? Okay, all right, so we're going to start with, we're gonna do Warshall's algorithm. Okay, so go to Geeks for Geeks. Type Geeks. Okay, good. Sorry, we want the Floyd's algorithm. So go to the Python 3 one.
Is this right?
That's right, yeah. Okay, we're gonna have to be careful because okay, good. Okay, we don't need the driver. We do need the
You want me to clean it up and like
let's get rid of the comments. Now, I believe it is okay, where is V coming from?
Oh, the
It's
Where
also
I don't know.
it's
Is
V
it-
also
over
the-
here.
Oh, it's a size? Okay, so we're gonna change
Yeah.
the V to len of the graph. Okay,
It's,
right. They're using capital V.
Yeah.
So let's change it. I prefer size. Let's call it size.
So I'll refactor it after, I guess.
Okay,
Like,
fine. You can leave it if you want. It's fine.
you want me to refactor?
Either way, rename size. Know what? I call it N. Call it N. Okay, good. Let's clean up the comments.
They also had some. I don't
We're
know
gonna
what
need
this
we're gonna need to do something else, but I'll tell you about that inf in a second.
is. Okay.
Yeah, what's that dist? Okay, get rid of line, those other comments there. Okay, move that all onto one line. Okay, good. Okay, we're also going to we don't need the Warshall part. Warshall is the transitive closure. You can just call it Floyd's algorithm. Floyd underscore, how about this? APSP for all pairs shortest path. Okay, good. And we need to do this though. We need to change.
Oh, there's a different function.
All right, we need to change the 0 to inf. Okay, so let's just create a function called we'll call it make non-edges inf. Good. Okay, and you could pass in a graph, and you could also pass in inf. So that's going to be our value of inf. Okay. Okay, so you could say you could probably do this in one line, but we'll do it in a loop. Okay, so you could say for I in range, len graph. Okay, and for j in range, len graph of 0, graph of I. Okay, good. You could say if graph bracket ij equals 0, then graph ij is inf. Okay, good. All right, so we're going to call this function at the beginning of Floyd. Okay, because Floyd is assuming that, oh, we should be careful here. Ooh, yeah, so we need to make a copy. Okay, we should never change the original data. So you could say, let's call it graph copy, or let's call it, yeah, exactly. Okay, and then in line, you know what, we could do it. Okay, fine. So just change it in 67 and 68. Okay. All right, this algorithm may be slow because it's an O of n cubed. But let's try it. How does a print solution look? Do we need to clean that up at all? So let's fix that print statement.
Mhm.
You can just say shortest distances. Well, we'll understand that. So shortest distances between every pair of vertices. Get rid of the following matrix. Okay, we understand that part. Just the shortest distance between every pair of vertices. Okay, you know what else we should do though? We should have the pred.
How's the inf passed here? It's not.
We don't need the, oh, you could hard code in on the top of the,
No. Okay.
very top. Hard code inf to whatever they hard coded it to.
It's
Okay, and then when you make when you call it, where do you call it? No, not there. Well, that too, but where else did you call it before?
well, we put it as a.
So you could not parameterize it, just make. Okay, good. Okay. You don't need those parentheses there. Okay, but we should compute the predecessor matrix. Okay, so in line, okay, you know what? Can we go to my slides? And instead of that list map, which is very confusing, let's do it the way we did it in my slides. Okay, so open up lecture probably like 10. The second graph algorithms. No, actually it's in dynamic programming. You got lucky. Go to the end of dynamic programming. Go to the end.
The end.
Yeah, should be towards the end there. So look for not knapsack, Warshall. Go up. Go one more. Floyd. Where's the go? No, go to the code for Floyd. Right there. Grab that init loop. That whole thing. Yeah. And put that into your Floyd. instead of line 69. We're gonna have 69. 69 is too confusing. Let's get rid of the whole 69. Paste. Okay, get rid of the word init loop. Okay, for I in range n. For I in range n, start at the top. No, you're gonna, okay. Just go in order. For I in range n. For j in range n. Okay. We need a distance. So you're gonna say this, you're gonna say before that, before the loop, you're gonna need to initialize distance. Okay, so you could say dist equals bracket 0, or better yet, we'll make it inf. No, bracket, another bracket. No, dist bracket, start, go back. Dist equals bracket and a bracket.
Okay.
Like that, INF, capital, because you're using the constant.
Right.
Okay, and you're going to do that times n. So after the first bracket, times n. Okay, and then you could say for I in range, no, still in that loop, still in that list. Let's go list comprehension. For I in range n. Okay, and do me a favor, put a print statement there of the dist. Good, okay. You can get rid of those comments there in 73 and 74. No, leave the code, just get rid of the comment.
Oh, sorry. Yeah.
Okay, move those lines up. Okay, those need to be indented. 1, good. No. I, right, okay, no cost, get rid of that comment. Okay, let's make sure that that looks good. So you can print dist and cred right before the for loop. Right over there, where your mouse is, no. After, move the print down after we've initialized it. Take it away from there. After the initialization. So go down to line between 75 and 76. Print dist. And outside the loop though. Print dist. And print pred. Okay.
Wait, pred. Yeah.
We need to
Okay.
initialize spread, right?
Oh, yes, make a copy of 69. Good, thank you.
What did you mean?
Make a copy of it, Control D.
Okay.
Okay, the only thing is, what are we going to initialize it to? So we're basically saying it doesn't have a predecessor. So let's use -1 instead of inf. No, instead of inf. Okay, let's try that. But we need to update the pred. So Control D on 82. And you're going to say pred ij equals, no, we need an if statement here. So for after for j in range, do it like in my code. For j in range, go up. If dist ij greater than dist ik plus dist kj Okay, then indent that. Indent that code that you have there. Dist ij is going to be equal to dist ik plus dist ik plus dist kj.
So I'm replacing this.
Well, you have the code there already. Just get rid of the min part. It's going to be equal to the dist ik plus dist kj.
Just like, okay.
Okay, good. And we need to update the pred. So it's in the slide also, but we know what it is. So pred ij equals the predecessor of k to j. Okay, good. Now, eventually, we're going to need to unindent the print solution, fix up the indentation. So 80 is over indented.
No, that's actually.
Wait. What are you doing there? Okay. And the print solution should not be in the loop. Okay. Okay, let us call that. So you can call that on the AM. Now you have, leave all that. That's good. Now you're going to call Floyd.
That's what I have to put into variable.
Call Floyd.
Okay.
Okay, run that. Okay, what is it complaining about? Okay, so that's going to be graph copy. Okay, run that again. So you could assign that, make it n equals. No, and make it, okay.
Yeah, I got refactor.
Whatever you want.
What is
So
what
it's going to be the len. It's the len of the dist.
should I refactor it?
Okay. That looks nice, right?
Mm-hmm.
Okay. Now, where should we put the pred? You want that in a separate matrix? We should probably print that out. So the easiest will be if we just print it separately. So after the print solution, go in the print solution. Let's call it print solution Floyd. And use an underscore there. Yeah, Floyd. Okay, good. Okay, and we're going to pass in refactor, do refactor. Okay, we're going to pass in dist and pred. And let's shorten the caption to dist matrix. Just dist matrix. Don't need shortest. Dist matrix. And then make a copy of this code. Okay, and then we'll say it's the same. No, it's in the same function.
In same. Okay.
And we're going to call it the pred matrix. Okay, we don't need line 101. And we're just going to do for now. Oh, you know what? We don't print the pred matrix. You know what we should do? You should print out the path, the shortest path. That would be cool. Okay. So how do we do that? So you're going to work backwards. You're going to work backwards. Okay, now don't get rid of that yet. Let's think about this for a second, right? So it tells you the predecessor. It tells you the predecessor. So we're going to say, okay, here's what we're going to do. Okay, in 103, get rid of that line. And we're just going to say P equals, so create a, before the print, equals pred I. Actually, let's create a variable before the for loop. Okay, so you're going to say P equals.
Before this for loop too.
No, between the two, right there. So you could say P equals J. That's the target. Okay, good. We don't know J yet. So it's P equals I. Okay, good. And now after the for loop, we're going to say right there, put your mouse, move your right there, move your mouse to the second for loop. And put a print statement inside that for loop. Print P, comma, and then make a backwards arrow, but inside a quote. Yeah, make maybe 2 arrows. It'll be clearer. Good. And do an end equals blank, like you have there. You say end equals, so that will make it not return. End equals, like you see on the next line. No, look how it's done on the next line.
Yeah.
That prevents it from returning. And then you're going to say P equals pred of, okay, it's going to be, let's see if this is correct. You're going to go the predecessor on the path from I to P. Yeah, so P equals pred IP. Okay, good. Get rid of the print statement on the next line. And then instead of the else, after the for loop is over, you say print. After the for loop is over. So unindent, good. There's a print. Good. Okay. No? Okay, let's run that. Oh, you know what? Okay, hold on. First, we need to pass in print solution Floyd disk, pred, line 685. You need to pass in both matrices. Okay, go down though. Go down, and I think when we print, so in line 102, oh, you have the I. Okay, I think that's good. Let's run it again. Okay, so let's try to understand this. Okay. Saying if you want to go, no, this does not look right. Saying if you want to go from 0
Yes, sir.
the old pair shortest path. It's not going to work like that. Okay, let's just copy the code for dist. So go back in there, copy the code for the dist. You're all over the place. Stay in one place. Copy the code for the dist in the print solution.
Oh, okay. For this one.
Well, you don't need that, or you need from the you need the loop. Right, the n isn't going to change. And just put that after the pred matrix instead of what we have.
So you want me to move this down?
Not move, it copy. Instead of what you have. Good, good. And change the dist to pred. Not there, no, in the pred code that you just copied.
Yeah.
Okay, and except we don't need the if statement. So you're just gonna say print. Oh, I see what they're doing. Okay, we don't have an inf, so just do print, get rid of lines 102, 103, 104. Just need one of those print statements. And we need a plain print at the end. But then you get rid of one of the 102, get rid of 102. And unindent 103. Good. And unindent 102. Stop. Okay, and fine. Let's run that. Okay, so this tells you, so for example, the way to read this is it's saying if I want to go from 0 to 0, I don't need to do anything. If I want to go from 0 to 1, I need to go to 3. See that? You're in the wrong place. Go down. Okay, you're in the pred matrix, right? So if I want to go from 0 to 1, I need to go to 3 before that. Okay, and what are those zeros there? What does that mean? It means there's no predecessor. What that means is I go from 0 directly to 2. Okay, can you put your mouse in the right place? Okay, move over one. Right, no, 0 to 2 is right there. Good, stop. No, put it back. That's going from 0 to 2. It's saying I go directly from 0 to 2. Move your mouse over one. Good. That's saying I go directly from 0 to 3. Move over one. Saying go 0 directly to 4. Okay, move to the next line. Beginning of the next line. Okay, that's saying if I want to go from 1 to 0, I go to 4 first. Okay, how do I get to 4 from 1? I go to 4. So you got to work backwards. All right, so this is sort of cool, right? We've got a matrix here, a cost matrix. Okay, what we should do is let's get a better print function for our graph. Okay, so why don't you make You know what you could even do? You could do print graph, copy, def, print solution Floyd. Just copy that whole function. And we'll just say call print graph. And we're just going to pass in a graph. Okay, we don't need 107. We'll change that to len graph. Okay, so you have here for I in range. In line 110, we're going to say if a graph ij equals 0, then we're going to replace it with inf, okay, because it's really inf. Okay, and in line 113, no, what are you doing? Undo.
Oh,
You
this
leave
is
that
in.
as it is. That's good. Okay, line 113, change that to graph. That's right. And then you can unindent, you don't need the if j thing. You need the print. So just take the print and put that unindent, right? So that's going to come after the loop. One more. Okay, get rid of the print pred matrix. Good. Okay, go down to your main. And before you print the APSP, why don't you print the graph? But use print graph now. Before the Floyd. Good, let's run that. So there's your graph. It's a little messy. Why is it a little messy?
Maybe you're saying this part.
I'm saying, why does dist look nice? Maybe because it doesn't have any infs in it.
Are we putting this?
Okay, I guess look at it. Let's look at it again. Oh, well, we lost the T. So in line 111, you need a /T. That's a tab. No, backslash. Yeah, and do the other one also. Where is the print solution? I think we lost a /T there. Okay, let's run it again. That's better. Okay, so again, this is a loop-free graph. That's a loop-free graph. So the diagonal are all infs. You like that? Yeah?
Is that supposed to be good? I don't know.
I think it's good. What's that thing beneath the graph, though? Where did that come from?
This?
Yeah, why is it being printed a second time? Where did that come from? So we're printing the cost matrix. Or are you printing the graphs? Is Floyd printing it? Maybe Floyd is printing it.
Oh, yeah, let's see.
Yeah, get rid of those.
These two?
Yeah. Okay. There we go.
So
Okay.
this is.
That's the graph itself. That's the cost matrix in a nice printable
label
form.
it?
You could put that. Yeah.
Be over here.
You could do it below. Do it in the main.
On the main.
Just don't do it in the same line. Yeah, so print cost matrix. Good.
Yeah.
Okay, nice. Okay, how are we doing on time? We have some time left. All right, we're going to do Dijkstra's algorithm. Okay, we're going to use we're going to do one for an adjacency matrix. Actually, you know what? Let's do Bellman-Ford.
Just copy. Oh,
Yeah, we don't need all that stuff there. Well, we'll change the function. It's okay. So
maybe just this one.
Yeah.
Okay.
Okay, so we're going to call it Bellman-Ford single source SSSP, single source shortest path. Bellman underscore Ford underscore SSSP. Okay, we need to pass in a graph. And we'll call it SRC for source. Okay, so we'll leave that as it is. Okay, so we're going to pass in the value of int, and instead of float, we're not using float, we're using int here. Okay, so line 137. Let's go in order. Okay, change that to int. Actually, we don't even need int. We could just pass in the constant int. Constant int. If you have a constant there, you have a constant. You don't need the int. Just pass in int.
So it'll be here, right?
Correct. Good. And we need to get, instead of self.v, let's create a variable n.
So
we'll create the variable first before you use it. N is going to be the length of the graph as usual. Good. Okay, we create our distance array. We initialize the distance to the source as 0. And let's create a. Okay, so we're going to say for I in range. No, use the code that's there. Use the code that's there and modify it. So you could say for I in range n. Okay. And you know what? Let's look at, I think I have code for this. Do I have code for this? I think I do. It's in Graph Algorithms 2. Otherwise, we'll figure it out, but. Should be towards the end, I would say. For that. Okay. Okay, you know what? We're going to use we made it, we might as well use it. Okay.
So this whole thing.
Hold on. Let's try to understand. All right, I guess we're gonna pass in the edges also. All right, so let's try that. So go back to the code, keep this open. Go back to the code. In addition to the graph, let's pass in the EM. Or what do we call it? The EM? What do we call it below? The ES.
Yes. Yeah.
Okay. Yeah, I would do that before the SRC because the SRC is the most specific, so just general parameters. So you got the graph. If you want, you could call it the CM for the cost matrix if you want. So instead of graph, just call it CM for cost matrix. Okay. All right. So you could say this, and instead of for UVW in self.graph, you're going to say for UVW in ES. Wait, hold on. No, you're changing things too quickly. Undo.
We changed C.
Undo.
Mhm.
Okay, UVW doesn't work on a graph. Okay, in line 141, it's UVW is in the edge set, right? So for UVW in ES.
I see.
Good. Now let's
Should I
go.
change these?
Don't change that yet. Let's look at 142. So we're saying if the distance of U is U plus W. Okay, you could do it like that. You could say if not equal to inf, from line 142, if dist of U is not equal to inf. Good, and dist U plus W is less than dist of V, then dist of V equals dist of U. That's good. And in 144, is this indented? Go back. This is the end. Okay. So you could do again for UVW in ES, and then again in line 145, if dist U is not equal to, this is where we not equal to inf, and dist U plus W, then it has a negative weight cycle. We don't need the return statement. Okay, and the print, get rid of that for now. For now, you could just print dist. On the bottom, no,
On the bottom.
no, put that back. You need that. You need to say it's a negative weight cycle. Instead of line 148. No, you don't need another print there. Instead of line 147. So just print the dist for now. Good. Okay, we might print it nicely later. Okay, so we need to fix line 137. Now you can switch 137 back to the cost matrix. Good. And anything else we need to do here? Are we using the cost matrix? Yes, just to know the size of the dist. Okay. Fine. Or are we using the I, or we're not even using the I? That's just a counter variable. Okay, let's run that. Now, let's just put a print statement there. So let's put a print before Floyd and a print before, so print Floyd's algorithm, Floyd APSP.
So we're printing this.
Wait, did you lose the print solution or prints it from the Floyd? Okay, right there, put a print statement.
Here?
Yeah.
Keeps.
Put on the next, no, on the next line. No, you can't print that. The function doesn't return anything. Before, you always put a caption before you do something, right? So So print Floyd APSP algorithm. No, it's a string. You're printing. There you go. Okay, good. Now get rid of the underscore, right? This is English, right? So APSP is abbreviation, all APSP. Caps, it's acronym, right? APSP, good. And then do the same thing for the Bellman-Ford. Now we're going to check it, okay? Bellman-Ford SSSP. Okay, SSSP, single source shortest path. All right. And we're going to call that in a loop. Okay.
Oh, we have to. So that the
you know what?
AM1.
You don't even need the CM there. We don't have any negative weights. Cheng Shi is asking a appropriate question. We don't have negative weights, but we should test for them anyway. So we will never have any. Correct. Okay, let's just do this. You don't need to pass in the CM. Get rid of the CM, but we will pass the N. So after the ES, pass N. Good. And get rid of that line there. Good. Okay. Go back down to what we call the Bellman-Ford. And wait, what its name should have SSSP in it. Check the name again. SSSP. Yeah, single source, shortest path. Okay, and we're going to call it with 1, just a source of 0. So you need the okay, so you need 3 parameters. The first parameter is going to be the ES1 because you're passing at the edge set. Second parameter is going to be the size, which is going to be the len of AM1. And the third parameter is going to be the source, which we're going to use 0. Now, if it works correctly, then what Bellman-Ford will print out, here, better yet, let's do this. Let's do a loop right there. Put a loop for I in range len AM1 colon, and then call that Bellman-Ford thing. Good, and pass in I instead of 0. Good. Okay, let's go up to the Bellman-Ford again, make sure it's going to print nicely. It prints it on 1 line. Okay, good. Let's run that. So we would expect that Bellman-Ford and Floyd come up with the same answers. Do they? Do they come up with the same answers?
Looks like it.
That's good. That's good. All right. Okay, how are we doing on time? You have 10 minutes left. Okay, so what you're going to have to do on your own is you're going to do Dijkstra's algorithm 2 ways. You're going to do Dijkstra's algorithm with a adjacency matrix and with an adjacency list and a heap. Okay, why don't we have 10 minutes left. Let's see if we can do the adjacency matrix one. So you have to look at what Geeks has. We might not like the version they have. Okay, well, it's not just adjacency matrix, it's Dijkstra, right? You can try that. Okay, go to, now which one, we don't know which one it's using. Okay, let's look at it for a second. Okay, I guess you're gonna need this and min distance. Those two functions. Okay, so let's change Dijkstra to Dijkstra underscore SSSP. Dijkstra SSSP. And get rid of that comment before. Big comment before. Good. And okay, fine. Okay. All right, so instead of self.v, go into that code. Okay, you're gonna clean this up first, fine.
Oh, where?
So in Dijkstra SSSP, you're gonna say n equals, at the beginning of that function, len of, we're gonna pass instead of self, you're gonna pass in the cost matrix. Okay, this one uses cost matrix. Good, len of the cost matrix. And in line 166, instead of sys.max size, you're going to use inf. Good, and instead of self.v, you're going to use n. Good. Line 166 is good as is. Wait, let's do one thing at a time. Line 166, okay, 163 is good as is. Line 164, you're going to do false. False are things that haven't been visited yet. So it's going to be times n. That means n of them. Okay, for C out, I don't really like for C out. Let's come up with a better name for that. So let's do for I in range of n. And we're going to find the minimum distance. Okay, so the minimum distance is not self. We'll call it Dijkstra min distance. Okay, it probably doesn't have to be for Dijkstra, but just in case. So go up, change the name of that to maybe, hold on, maybe you don't even need Dijkstra. Maybe it's really self-explanatory. Let's just call min dist. Okay, refactor. Okay. All right, let's see what we need. So we need the SPT set. That name has got to go, but I don't know what to change it to yet. Let's get rid of the self. We don't need the self, I don't think. Go to line 149. Get rid of the self. Okay, n will be equal to len of dist. Good. Get rid of 151. Don't use min because min is also a function. So you could say mn if you like, or better yet, min d equals inf. Okay, and then you could say for u in range n. Okay, if dist u is less than min d and SPT set. Let's change SPT set. I really don't like that. Visited. Or done. You could call it done. Okay. And you could say and not done. That's better Python. And not done. That's good. Then that becomes the min. The min index is the position, fine. Okay. Okay, let's create a min index at the beginning. I'll put it right after the min D. Move it to after the min D.
Ooh, sorry.
Move that line after the min D. You could see if it'll let you change the min D to min dist. No, that's the name of our function. Change it to min dist.
This.
Just change it to min dist. Okay, and the min index, you make it to -1. You could change the name of the function to min distance and make the variable min dist. To forget the refactor, well,
Yeah.
Okay, change the min index as -1. That's good. You go to the range of n. Okay, you need to change line 154.
Yeah.
Good. Good. Okay, now we come back to the Dijkstra. Okay, we're going to change the name of SPT set to done. Line 164. And change it in 166. Okay, and in line 169, you can say and not done. Get rid of the false. Move those onto the same line. And now that's part of the same line. 170 is part of 169. It's not
so.
Okay, so and not done, and get rid of the equals false. That fix was good, what we did. And not done, and the distance is bigger than, okay, instead of self.graph, you're going to say CM for the cost matrix. You got it again on 169, at the end of 169. At the end of 169. Good. Okay, and are we printing the solution here? We'll print the solution later. Okay, so get rid of line 171. And I guess, what did we do in the other one, in Bellman 4? Did we return? We printed dist? Okay, so you could print dist here. You could print it here in Dijkstra. Good. Okay, I think we are ready to roll. That was pretty good. Okay, so copy those 3 lines of code. Lines 1, yeah, exactly. So Dijkstra SSSP. Okay, get rid of the Ford, good. And just change the function name of 191. And we don't need the edge set for this one. You do need the CM, the AM1. We called it AM1. You don't need the len. Okay, let's run that. We expect them to get the same answer. Good. You get the same answers?
Yeah.
All right, isn't it nice when things work?
Mm-hmm.
Okay, thank you. Thank you, perfect timing. All right, so you've got one thing left. I'm gonna make a formal assignment, but you have, well, 2 things left. Number 1 is you got to code Dijkstra using adjacency table. So you already have the adjacency table, now you're going to use it with adjacency table. And this is all part of the same thing, adjacency table. Where are you going to the next line? Go back. adjacency table plus, no, adjacency table. Don't write adjacency table. Plus
I was just making a note for myself.
binary
Yeah.
heap, binary heap. Okay, good. All right, once you do that, you're gonna run it like we've been doing in our other assignments. Okay, which means I want you to run it, over a loop. And then you can plot it. So instead of having 10 sorts, you have 3 algorithms to do this. Actually, you have 4 algorithms to do the same thing. Okay. So you have 4. You know what? It's not really fair to use the Floyd. Okay. So you're going to use Bellman-Ford and the 2 versions of Dijkstra, and you're going to compare them. Those are going to be your 3 algorithms here. So you're going to use the template we have, right, for all those code, and those are going to be the 3. We've got to put the URL where we got the code. We could do that, yeah. It's a good idea. I mean, we changed it a lot, but if you want, you could put that in. Just grab that. That's good. Okay, and the Bellman-Ford. That's Floyd-Warshall. So put that in before the Floyd-Warshall. Good. And we had one more, right? The Bellman-Ford.
Yeah. Don't know where we.
Okay. Nice job. You're not gonna need the text table for this one. You can get rid of that.
Where was that?
Text table from the previous assignment, we're not gonna need that. So you're gonna need to move in your template from like assignments 1, 2, 3. Each sizes trails. Oh, trials. Yeah, you should try it for a few different sizes. You don't need trials. I don't care about the trials in this case, because the time, but you do need the, you can delete that. You don't even need to save that. Okay. So you don't need trials. You can make trials equals 1 if you want to leave the trials in there. But you should try it for different sizes. Okay, I don't know how far it's going to. Well, you need to get that code from.
Right, yeah.
Look at assignment 3. Okay, look at assignment 3. Okay.
Yeah.
Very good. Okay, nice job.
Thank you.
Can you go down to me? There's some.
Right. By the way, you
post
could
this.
comment. You could comment out line 171 if you want. You need the prints. You can get rid of comment out 173 and 175, and that you should keep. The rest you should keep. Okay. Now, if you're running it for different sizes, you don't necessarily have to print out every single result, for me, because I really want to see, let's say 1 to, okay, so what you did here was great, because you've got Floyd, got Bellman-Ford, you got Dijkstra, and you see that they're all getting the same numbers. That's good. You understand?
Yeah.
But you don't need to do that for every single size. If you do it for 5 and it works, you've convinced me. But then we also want to track the complexity, right? And see which of these 3 algorithms, so you've got the Bellman-Ford, you got the Dijkstra with the adjacency matrix, and the Dijkstra with the adjacency table and binary heap. Which one does best? We would expect the last one, but sometimes we get surprises. Okay, and you can leave the Floyd in for good measure, but that's not really part of your trial because it's not fair. That's an n-cubed algorithm. So you can leave it in for the printout, but don't put it in the graph because it's a different order of magnitude. Right? Okay, well done.
Should I post this on the Slack?
It's up to you. I think your classmates will like you. They still have to figure out Dijkstra. So if they didn't understand anything that was going on today, they'll have a hard time, but so you could post it.
Okay.
All right. Thank you. Appreciate your volunteering again.
Yeah. Thank you.
Good job. Okay. Okay.
Oh, do you have time for some questions afterwards?
A question? I have time for a question. Yeah. A little bit of time. Then I have a class, but
I was just wondering for assignment 6,
yeah.
if that's okay.
Yeah.
I was just wondering how we're supposed to pass in, like if we have to pass in 3 different files, and how are we, like, how are we
Okay,
looking
so
for?
when you're processing a file, I don't think you would process a file with 2 different text file names. I think you would want to call that twice. You agree with that?
Yeah, but like, are we reading each line? Are we looking
So
for those
someone asked
patterns?
it on the Slack. So the text file is one big string, right? It's the Star Spangled Banner. It's the the Gettysburg Address, right? So that's one big string. It's one big text, and the pattern is individual words.
But I mean, the process file method that we had from the other assignment, it was going to read line by line, so it would have like a
So
list
forget
of
other
lines, right?
assignments. Let's do what makes sense here, okay? So you've got string matching is text and pattern. So what you're doing is, I would call process file twice with text file once. Understand what I'm saying?
Mhm.
Okay, if you, here, do you mind changing this? You
No, I
okay
don't
with me walking with work? Okay, so get
Yeah.
rid of text file, just change, get rid of one of those. Okay, and we're going to call it text file name, and get rid of the second with open. No, not that one. No, sorry, I misspoke. The second text file one. Go down, get rid of that whole block there. Okay, let's change line 149. By the way, the encoding is what? The encoding is the wrong encoding? You need to fix it?
No, this works.
That
I
encoding
just copied
works?
this.
Okay, so change line 140 to text file name. All right, so pattern lines is a list of lines. That looks good. Okay, 141 should be text 1 equals file dot read. Text 1 equals file dot read. Okay, and then you're going to say for line in patterns. I'm sorry, for line in pattern lines, sorry. Better yet, why don't you call line 139, call that patterns? Well, patterns. Good. And then in 143, you say for pattern in patterns. And I would indent, because this really isn't part of that business anymore. Unindent that, unindent those next lines there. Okay, now what's the regular expression about? Do we have,
This is.
is there garbage in there? Get rid of.
I don't know.
Okay, get rid of line 142. I don't think you need 142. Okay, so tell me what you're doing. Are you converting it to uppercase? Okay, do we need to? We might, maybe you're right. Okay, and we're getting rid of non-alphabetic characters. Fine, I'm okay with that. Okay, in line 143, change that to pattern equals pattern dot upper. Pattern equals pattern dot upper. And you know what? Let's fix text. Actually, is there any reason you can't leave that stuff in? Okay, go up. Let's change the text to upper. I would agree with that.
Text.
So in line 141,
Mhm.
you could say file.read.upper. No, file.read, no, you read as a function. You need the things there, dot upper, parentheses. Upper is a function as well. And line 143, you lost an N there. Okay, and then I don't think we need to remove non-alphabetic characters. Do we have any?
I mean, spaces, I guess, are
No,
spaces
but
considered?
no, because we don't want to find it if there's a space, right? So the man and the men are not the same thing, right? So I would leave that. I would get rid of line 144. And get rid of line 144. Okay, and if you want, you could trim the pattern. So you could do what's the term? It's not called trim. What do they call it in? Anyone remember it in Python? It's not trim. What do you do to get rid of the garbage on it? Or white space. How do you get rid of the outer white space?
Should I look it up quickly?
Sure. Remove white space. Not split. It's not split. Strip, that's it. Okay, so if you want, you can get rid of the outer white space. So do that in line 141. It's a function, and do it in line 143. Okay, and now you're ready to call your function. So you have a pattern, you have a text.
Mhm.
Call your function.
I don't know what happened here. This is
That's all your stuff left over from the previous.
yeah. So I guess
You're basically calling those, right?
yeah.
But you want
So I would
to put it into your framework, right? So you're running over these different algorithms. So if you want, you can just, right? So this is running it individually. You need to set up, get your infrastructure from your previous assignments, right?
yeah.
Except instead of running for different sizes, you're just going to run for the different examples that I gave you.
Yeah, I have to,
Okay, so if you want, you know what I would do here? I would just maybe just return the trial and the pattern. So
so the pattern. Oh, result. I was gonna put it in result.
you could just return. Well, you got to be careful. You're going to clean up the patterns. So you could do this, okay? On line 142, say for I in range 142, for I in range, len of patterns. Good, and now in line 143, you're going to say pattern of I equals, patterns of I, sorry. Patterns of I equals, patterns of I, yeah. Okay, and now you can return text, comma, patterns. Okay, so that's how you get your stuff.
So wait, this is like a list.
Well, it's two lists. Oh, it's a string and a list. So you get rid of 137. I would also suggest flipping the order of move 137, 138. To after the other one. It just, the order makes more sense that way. And you could even move the loop, indent 141 and 142. Make that part of the width is even better. Good. Now get rid of 144. What's that ... going on there?
Oh, this is, I just commented out, like, I guess, old stuff. I probably don't need it.
I would follow better to follow the example you have in another assignment. So basically,
Okay,
instead of
so-
iterating over sizes, you're going to try it with your different patterns.
Mhm.
And
Okay.
either you do the two files in one graph or the two together, and you can put them into one, combined image. Just paste them into one image, because you're going to have one place to upload it. All right.
So this is
All
going
right.
to look,
I got to run. I got another class. All right. So
Okay,
that'll
yeah.
get you your
Thank you.
text and your file, your text and your patterns, and you use those in your main. You'll need to go back, grab the template.
Mhm.
Right. So the
Okay.
code you have there is just, that was for testing, just like we did in sorting. We tested the sorts individually before we worked it into our infrastructure. Okay.
Yeah, okay,
Good.
thank you.
All right.